my name is Dana Golden. Today we're going to finish up our look at the economics of nuclear power with a look at the basic costs of nuclear power. So the costs you learn about when you think about nuclear power costs, first off you learn about total construction costs, site preparation, reactor construction, auxiliary facilities. Then you look at financing costs and lead time. Long lead times increase costs due to interest during construction and the cost of interest rates as interest rates rise. Because nuclear has high fixed costs, nuclear becomes less desirable as interest rates rise. Then you have operation and maintenance costs, routine maintenance, staff salaries, and safety upgrades. Most of this is the engineers you're hiring to actually run the plant. And then you have fuel costs, which are a very small fraction compared to other power sources. Obviously, this doesn't include renewables, where fuel costs are basically nothing. Yeah, it's a small fraction of nuclear power costs come from fuel. And then you have decommissioning and waste management costs, which are incurred at the end of plant life. And then you have total construction costs, key components to direct costs, reactor turbine, cooling systems, indirect costs, engineering project management. And then the equation for the total cost of construction is the sum for I, where I is the period of direct costs in each period I plus indirect costs in each period I. Or sorry, not the period. Those are the product component. Where these are the direct and indirect costs for each composite component, and N is the number of components. And then the biggest drivers are regulatory requirements, labor costs, and materials. Regulatory compliance is a big part of what makes it so costly to have nuclear in place. And then, of course, you have financing costs and lead time. Financing costs include interest accrued during the long construction period. So to get this, get financing costs F, this is the cost of construction times the annual interest rate times the construction time in years divided by 2. Lead time directly impacts the overall cost. Cost total equals the cost of construction plus the financing costs. And the importance of minimizing delays is very much up there to reduce costs. So you don't want to spend a ton of time taking it, because now that discount rate means that those dollars are valued less, and now you've spent more on financing. Operation and maintenance costs cover upkeep, safety inspections, and salary for employees. So this is operation maintenance costs is fixed operation maintenance costs with variable operation maintenance costs. Fixed costs are independent of the power output. You have to pay the engineers. You have to pay for insurance regardless of how much power you're outputting. And then variable operations costs are dependent on power output. You usually have a diesel generator at the renewable power plant to get the thing going. So this is pretty variable. No, I didn't say get the thing going, to power the plant when it's offline and whatnot. And so this is consumables and repairs. So this is dependent on power output. And then you have regulatory compliance and plant agent efficiency drive how much operating and maintenance cost you have. If you have stricter regulatory regimes, you require more operating and maintenance costs. If you have more efficient plants, you have lower operating and maintenance costs. If you have older plants, you have higher O&M costs. And then the capacity factor measures how effectively a nuclear power plant generates electricity compared to its maximum potential. Capacity factors are the reason why nuclear is such a desirable energy source, despite all of its other problems. So, of course, capacity factor is the actual energy generated over the maximum possible energy. So the actual energy generated is the energy produced in a given time period, and the maximum possible energy is rated capacity times hours in the time period. High capacity factors for nuclear plants, most of them are 92% is the number I always hear, and almost all of them are 90% or higher. So key drivers of high capacity factors, they're used in baseload operation because they have such low variable costs. They can run pretty much continuously because they pretty much always make it into the market. They always bid into the market, and they're almost always below LMP in terms of marginal cost. And reliability, there's fewer unscheduled outages. That 92% actually is almost always, like a nuclear plant has to be offline for 8% of the year, usually about 2 weeks. Just clean it up for regular maintenance. So remember, capacity factor nuclear is higher than capacity factor wind, is higher than capacity factor solar, and higher than capacity factor of coal. And so the levelized cost of energy, putting it all together. Here, a lot of people call it levelized cost of electricity. In this case, it's the average cost per megawatt hour of electricity. That's the levelized part. So you have a cost of energy, and then you have levelized is taking into account electricity generated over the plant's lifetime. So usually levelized cost of energy and levelized cost of electricity are used interchangeably. The reason why nuclear in particular has this levelized cost of electricity is because you can use nuclear plants for other things than just generating electricity. Sometimes people use nuclear plants for, say, desalinization, because it's a great way to generate the power needed for desalinization. You have LCOE equals, you have the sum by all time periods, cost of construction, which we calculated before, over the interest rate raised to the number of periods, plus the cost of operation and maintenance for each period raised over the interest rate, plus the cost of fuel over the interest rate, plus the cost of decommissioning. Usually this comes in later over the interest rate. And then you divide this, because you're levelizing it, by the electricity generated divided by the interest rate, because you're discounting future electricity. So R is the discount rate or interest rate, and T is the plant lifetime. So simplification using capacity factor, you can solve for electric generators capacity times capacity factor times hours in a year. So that will give you the electricity generated, which goes right there. And then high construction costs and long lead times increase LCOE. High capacity factors reduce LCOEs. This is why I went through all that on the physics and on the technology behind this, is because the technology, and this is true for nuclear, but this is also true for any other technology where you're looking on the investment. The technology drives how good an investment it is. So really, if you want to analyze a power source, you have to understand what goes into that power source and how that affects the techno-economic analysis. And then you have the capacity recovery factor, which converts the upfront capital cost to equivalent annual cost over the lifetime of a project. So the equation is CRF equals R times 1 plus R raised to the T over 1 plus R to the T minus 1. R is the discount rate and T is the project lifetime, and the annualized cost is A equals C of capital times CRF. C of capital is total for upfront capital cost, and then A is the equivalent annual cost. The capital recovery factor is how you can transform this cost of capital into an annual cost to basically take into account the fact that you're putting all these costs up front, and then you're getting the power after you built the plant essentially for free. So capital recovery factor helps you think about this in an annualized way, how much it's costing per year rather than upfront and then essentially zero. Capital recovery factor, so you have C of capital, we'll assume 10 billion, probably. That's probably about right, actually, for the plants you're developing now. So R equals 5%, T equals 40 years. 0.05 times 1 plus 0.05 to the 40, 1 plus 0.05 to the 40 minus 1. This is using LCOE calculations to distribute capital costs over the plant's lifetime. So the idea here is that you're taking out the loan, so you're not paying the capital costs all up front. So you don't want to put the capital costs into the LCOE all up front. You want to distribute it out over the entire lifetime of the plant, because that makes the economics a lot better, and because the loan is paid back over the lifetime of the plant. So decommissioning costs in the nuclear trust. Decommissioning costs are incurred at the end of the nuclear plant's life, and includes dismantling the structure, safely disposing of radioactive materials, aside for restoration. Typical cost ranges 300 million to 1 billion per plant, so pretty normal. And then the nuclear trust fund ensures that once you get to the end, you have enough money set aside to fund decommissioning. Funds are set aside in the operational life. Actually, you start setting aside funds, I believe, once you break ground, but even before it's operational. And then as part of the regulatory requirements to ensure sufficient resources are available when you need to dispose of it. And then investment growth reduces the upfront burden on ratepayers. So basically, you put the investment in a trust fund, and you have it grow because you're investing in interest-bearing or long-term assets. So here you have f of t equals f of 0, how much you really put in, plus its growth, plus C annual, which is the annual investment in the nuclear trust fund, times the rate of growth times the number of years since that last investment. And then finally, so that's how you think about cost as a whole. And then you also have the ability for different technical factors to impact your cost analysis. So nth of a kind models for new nuclear capital costs. Capital costs for nuclear plants decrease as more units are built, leveraging learning effects and economy of scale. First of a kind models acknowledge that there's higher cost due to initial design, regulatory approvals, and lack of standardization. And then you move to NOAC or nth of a kind. We have lower cost for subsequent units due to learning and replication. And so you have cost reduction dynamics where you learn by doing, reduces the cost per unit, allows you to build these things more cheaply. And then standardized design, simplify construction, and you have supply chain improvements. Basically, people are learning how to build nuclear plants. The first one was very expensive, and then everyone after that has a much lower cost. This is if you have the same designs. In the United States, traditionally, and I'm banging my head against the wall. I don't know if you can hear that, but I'm banging my head against the wall right now. So be concerned for me. Yeah, but in the United States, traditionally, we've always built a new nuclear plant. We've always put in a new design. We've never really gone out of our way to replicate the designs. And that's really increased cost overruns. We've basically figured out now, actually, we need to have a workforce that knows how to do a specific thing. And the NRC has done a lot to move forward with designs that can be implemented in multiple places. So when you're doing an nth of a kind model for new nuclear capital costs, this equation for cost reduction, the cost of the nth unit is the cost of the first unit times n raised to the negative of the learning rate. So n is the unit number you're learning over time, and then you learn at some rate greater than 0, so the costs decline until they get down. So applications. Policy support for multiple plants can accelerate cost reductions. So you want to approve a fleet of nuclear so that there's things for, one, an employable workforce to keep their knowledge and keep working on, but two, so that you can produce parts at the same time and just put it up. It reduces financial risk for developers at the time because they don't need to worry about, well, what if one plant is too expensive? Actually going to be building a bunch of them. It's critical for competitive advanced nuclear technologies. France, I believe, is very good at putting out a lot of the same nuclear power plant as is Japan. So comparing cost structures from traditional versus new nuclear. Remember, new nuclear, I'm talking about small modular nuclear reactors and more advanced reactors like those that are powered by thorium. Traditional nuclear power plants, large-scale reactors, differ in cost structure and economic considerations. So here's a little chart of how they differ. Traditional nuclear has very high capital costs driven by custom design and scale. We can fix this. We can build less customized reactors. New nuclear has lower costs due to modular design factor reduction. You're producing the same reactor over and over again rather than producing a bunch of different custom ones. Traditional nuclear has long construction time and high financing costs because of the long construction time. New nuclear has much shorter financing cost or shorter construction time, so they claim. We haven't ever seen a commercialized one, but the ones they built over at the national labs have had shorter construction time and then reduced financial risks. Traditional nuclear has high operation maintenance costs due to complex systems and large workforce, and then new nuclear has lower O&M costs because you need fewer staff and automated operations. I was trying this summer, I was working with some people, and I was trying for a report to calculate how many staff you'd need on a new nuclear plant. I didn't have, all I had to go was research papers, and I, got this number. It was, 30, and I was like, that's a really low number of people. You realize if they all get the flu, we now just don't have a nuclear plant? That's, scary. Anyway, so, a very small number of people needed by new nuclear, which is great from a cost perspective, but is kind of scary from the fact that these people, someone has to be there all the time perspective. And then decommissioning costs significant due to large-scale waste management. And then new nuclear is smaller due to smaller scale, which leads to reduced decommissioning costs. A lot of these are molten salt reactors, or potentially will be, so there'll be lower decommissioning costs. And traditional nuclear is designed for base load operation only, whereas new nuclear can maybe follow variable demand. And so the problem with traditional nuclear, part of it is that you can't have too many of them because they all have to run. And if they all have to run, you overwhelm the grid. New nuclear, that's not really a problem. It's more flexible, and so you can potentially have it as a variable resource in the same way you'd have some of the other resources like natural gas. So it acts as base load, but can also act as a variable. So key implications: new nuclear designs aim to lower upfront costs, improve ongoing lower upfront and ongoing costs, and improve economic feasibility. Short construction times, reduce financial burdens, and the modular designs allow for incremental capacity additions. So when I talked about going back here, when I talked about the rail belt and I talked about Anchorage, Alaska, that was a solution. That was a solution that was talked about for powering the rail belt, is potentially having a small modular reactor on site. That's also a solution a lot of people are talking about in terms of data centers and really big AI centers, and is have a small modular reactor that only powers you. And so you have carbon-free electricity, but you don't have to worry about anything else going on in the grid. So levelized costs and cost risk in a generator portfolio. Portfolio generation planning considers not only levelized costs, but also cost risk. So when you're thinking about a portfolio, not just having one asset, not just having a nuclear plant, but having maybe several nuclear plants, but a nuclear plant and several other plants, diversification reduces exposure to volatile fuel pricing and construction delays. So levelized cost calculation, portfolio LCOE, is the sum for each of the generators, each of the generators in the portfolio, of the weights. I guess in this case, number of generation types. You could, in this case, they've assumed that all the same generation types have the same cost. So weight the shared generation of each generation type or each generator times the LCOE of that generation type or each generator. And then you have an example portfolio. In this portfolio, we have some amount of nuclear, 40% nuclear, 40% gas, 20% renewables. Let's go. You also have nuclear. It's high. It's always high despite the low capacity, the really high capacity factor. And really low variable costs. It's very high because of the fixed costs. And then natural gas is a little bit lower, and LCOE for renewables tends to be the lowest, particularly if you're out in the middle of the country. The portfolio LCOE is 0.4 times 70 plus 0.4 times 50 plus 0.32 times 20. And then you can calculate how to think about the uncertainty by looking at the volatility from fuel price uncertainty. Maybe gas prices are very volatile. Maybe you don't know what the weather's going to be like, and that'll affect solar, and you don't know what demand's going to be like. So nuclear and renewables can provide stability to fixed costs and no fuel dependency. So if you have a gas generator, if you're a natural gas company, you want to own maybe some nuclear and some renewables in the portfolio, because a lot of the skills you have are transferable, and because it's very useful to be able to think about controlling the potential variability of gas with nuclear and renewables, which have kind of opposite risks. So portfolio variance combines individual cost variances. So the variance of the portfolio is the weight of each of the objects in the portfolio squared times the variance. This is just a traditional variance formula. You're taking the variance of a linear sum of random variables is equal to the constant in front of the random variable squared times the variance, and then you have to add in the covariance, 2 times the covariance, which is the constants multiplied by each other by times the correlation times the standard deviations multiplied by each other. Basically, you want to get the covariance addition. So rho is the correlation between costs of risks of generators I and J. And so the implication here is that a balanced portfolio reduces cost volatility, and nuclear can add stability to a renewable portfolio, and it can add stability to a natural gas portfolio, but it reduces long-run costs. I hope by this point, thank you so much for coming to this lecture, but I hope by this point you understand this lecture was not really about nuclear. Yes, nuclear is becoming important. Yes, I want you to be able to do things with nuclear. But really what this lecture was about was showing you how to think about techno-economic analysis, how to think about how the technology relates to the economics, so that if your boss asks you, listen, I'm thinking about putting a geothermal plant out in the middle of Montana, you can not just look at him with a blank stare and say, well, we need to think about these things that affect the costs that are part of the underlying technology. I'll look into those. I'll look at the research. I'll look at some site studies that have been done around there, and I'll put you together an LCOE analysis, and you'll make your boss happy, and you'll get promoted, and then you'll be the boss, and you can tell your junior analyst to analyze whatever you want them to. Have a great day. Thank you.